We present a noise-aware training paradigm for video saliency prediction. We want to train a deep neural network to predict a saliency map for each input video frame. The target saliency maps used for training are reconstructed from captured human gaze data. These maps, shown on the right, indicate the per pixel probability of attracting human gaze. Existing saliency prediction methods are affected by two main issues. First, the existing saliency datasets contain videos with limited temporal dynamics. Training on such datasets is ill-suited to predicting video-specific aspects of saliency. Therefore, we introduce Forged, a highly dynamic video game-based saliency dataset. Second, capturing video saliency data itself is difficult. The accuracy of a measured saliency map depends on the scene complexity and the number of available observers. For example, in this simple scene, the viewers focus their attention on the only object of interest, leading to a consistent gaze behavior and a unimodal saliency map. The inter-observer consistency converges quickly to its asymptotic value with increasing number of observers. For this scene, an accurate saliency map can therefore be obtained from the gaze data of just a few observers. Things are different for complex frames containing multiple objects of interest. The inter-observer consistency in this case converges slowly with increasing number of observers, leading to higher inaccuracies when only a few observers are available to measure the saliency. Overall, the accuracy of the measured saliency maps varies with frame content for videos of dynamic scenes, especially when few observers are available. Given the measured saliency map from human gaze data, traditional training directly minimizes the discrepancy d between the predicted and the measured saliency maps. When training gaze data from only a few observers is available, this direct minimization can lead to noise overfitting. Instead of directly minimizing for d, we first estimate its probability distribution induced by the presence of noise in the measured saliency. We then use a maximum likelihood approach to derive a loss function that takes into account the presence of noise explicitly. Our approach downweighs frames with high noise level, reducing their importance during training. This leads to reduced overfitting when noisy or limited training data is available. We now provide an intuition of our NAT loss function and refer the readers to the main paper for details. Recall that the accuracy of the measured saliency map depends on the number of available observers and the scene complexity. A discrepancy measure between the measured and the predicted saliency map would therefore be a noisy estimate of the true discrepancy when insufficient data is available to reconstruct the measured saliency map. We want to estimate this level of noise in the discrepancy measure. To do so, consider an n-observer measured saliency map. We sample n spatial locations from this map and reconstruct an approximation of the measured saliency map. We repeat this process multiple times to obtain several approximations of the measured saliency map. We measure the discrepancy between the measured saliency map and each of its approximations to obtain the expectation and variance of the discrepancy values. When the value of these statistics are low, the n-sample approximations of the measured saliency maps are highly consistent. This points to a highly consistent gaze behavior of the n observers in the measured saliency map for the given video frame, making this frame a reliable one for training. The reverse interpretation holds for an unreliable frame. During noise-aware training, we use this interpretation to downweigh a noisy frame based on the variance and minimize the discrepancy between the measured and the predicted saliency map only until it matches the expectation. To compare NAT against traditional training, we trained VNet on the LIDOV dataset multiple times for both approaches, with varying the number of observers used to reconstruct the training saliency maps. The average KLD and AUC on the entire LIDOV test set is shown here as a function of the number of observers used for training. When limited gaze data is available for training, NAT offers a significant advantage over traditional training across multiple experiments. In conclusion, we introduce a highly dynamic video game-based saliency dataset and a noise-aware training paradigm for video saliency prediction. NAT enables effectively training with limited gaze data. Given its robustness to inaccuracies, NAT ushers in the possibility of designing future video saliency datasets with fewer observers per video.